Welcome back to Bugs and Beyond, everyone. Before we dive into all the nitty-gritty, I think it's kind of cool to just take a second and think, wow, we live in a time where we have these awesome medicines.
It really is remarkable, isn't it? Like, imagine being alive a century ago. Something as simple as a cut could turn fatal, because of infection.
Exactly. But now we have these amazing discoveries like, well, the one we're talking about today, penicillin. I mean, it really changed everything, didn't it?
Oh, absolutely. It's the granddaddy of antibiotics, revolutionized how we treat infections.
So today's deep dive is all about penicillin, how it works, what it fights, and why it's still so important today.
Yes, like a plan.
All right, let's go back in time for a sec, back to 1928.
Ooh, a history lesson.
Picture this. You're Alexander Fleming, hanging out in the lab.
Yeah.
Petri dishes everywhere. And you notice something weird. There's this mold growing on one of the plates, and it's actually killing the bacteria around it.
Talk about a lucky break. Serendipity at its finest.
Right. That was the light bulb moment that gave us penicillin.
Yeah, but it wasn't all smooth sailing from there. Figuring out how to actually isolate it and produce enough to use, that was a whole other challenge.
Totally. I can only imagine what that must have been like.
Oh, it was a real process. But that's science for you, right? So want to get into how it actually works?
Let's do it. Break it down for us. How does penicillin actually, take down bacteria?
All right, imagine bacteria as tiny little cities, right? And they have these walls made of peptidoglycan, which protect them and keep their shape. Now, penicillin's like a saboteur.
Ooh.
It sneaks in and messes up the construction of these walls. It goes after an enzyme called transpeptidase, super important for building and keeping that peptidoglycan layer strong.
Gotcha.
And without strong walls, well, the bacteria become weak and eventually just burst. Kind of like a city with crumbling defenses.
Wow, so it's like a tiny demolition crew.
Yeah.
Just takes those walls down.
That's a great way to put it. And here's the cool part. Penicillin only goes after bacterial cells.
Good thing for us.
Exactly. Our human cells don't have those peptidoglycan walls, so penicillin leaves us alone.
That's definitely good to know. So there are different types of penicillin, right? Like penicillin G and penicillin VK.
You got it. Those are the natural penicillins, the OG versions.
The originals.
They work against a lot of different bacteria, especially those called gram-positive bacteria. They've got those thicker peptidoglycan walls.
So they're like the cities with the extra strong walls, and natural penicillins are good at breaking through.
Exactly. But here's the thing. There are some challenges with those early ones. Like penicillin G, we mostly give that by injection because it breaks down easily in the stomach.
But we wouldn't work so well as a pill.
Not really.
Yeah.
Penicillin VK, on the other hand, that one's more stable in stomach acid, so you can take it orally.
Makes sense. It's like it has a shield to get through the stomach.
I like that. But even with VK, absorption can be a bit iffy.
Interesting. So even how they're given can make a difference. Okay, before we get into how scientists tackled those challenges, how about a little top quiz? Test our knowledge so far.
Hit me with it.
All right, here we go. What's the key Y factor that determines how effective penicillin and other beta-lactam antibiotics are? Is it A, reaching a high concentration in the body, B, keeping the concentration above a certain level for a while, or C, having a large area under the concentration time curve? Take your time, think it through.
Don't rush it, folks. It's a biggie.
All right, time's up. The answer is B, keeping the concentration above the minimum inhibitory concentration, MIC for short, for long enough.
But why is that so important? It's not just about how much gets there, it's about how long it stays there.
So it's like a marathon, not a sprint. That keep those levels up to win the race.
Exactly. If the penicillin level drops below that MIC, the bacteria can start partying again, even if we had a big spike earlier.
Gotcha. So steady wins the race against bacteria.
Speaking of challenges, though, some bacteria have learned to resist penicillin, right? How do they do that? It's like they have their own little defense systems.
Oh, they're tricky little guys. One way they do it is by making an enzyme called penicillinase.
Right.
Basically, it's like a Pac-Man that chomps up the penicillin molecule and makes it useless.
Oh no, they're fighting back. But we didn't just give up, right?
Never. Scientists came up with penicillinase-resistant penicillins.
Yay!
These guys were built to handle those penicillinase attacks, meaning they can still get to their target and knock out those resistant bacteria.
Go science. So what are the names of these penicillin superheroes?
We've got oxacillin, nafcillin, and dicloxacillin. Think DON, like don't mess with these penicillins.
Love it. A warning to those bacteria. So what makes these guys different from the originals, better at fighting certain infections?
They're more specialized, yeah.
Yeah.
Natural penicillins are good against a lot of bacteria, but the penicillinase-resistant ones, they're the Staph aureus specialists.
Ooh, taking down the tough guys. Exactly. They're super important for those staph infections, which can be, well, from skin infections to pneumonia to even some serious stuff like endocarditis.
Wow, so they're key for some pretty serious situations. But
Yeah.
I guess even with these powerhouses, there can still be side effects, right?
You bet. Even the best meds can have downsides. But good news, there's a mnemonic for remembering these. Think hang, like those side effects are hanging around, just waiting to cause a ruckus.
Hang, I like it. Catchy. Breakdown time.
Yeah.
What does each letter mean?
Okay, H is for hepatic. Penicillins can sometimes mess with the liver.
Got it. Got to keep an eye on that. What about A?
A is for allergy. Probably the most famous side effect, right?
True.
Not everyone who thinks they're allergic actually is, but a real allergic reaction, well, that can be scary.
Always got to be careful with those. What's N for?
N is for neurologic. It's rare, but penicillins can cause problems like seizures, especially with high doses or kidney issues.
So watching those doses is important. And G?
G is for gastrointestinal, upset stomach, nausea, that kind of stuff.
Right, the usual suspects.
Yeah.
So hang covers it all, from the mild stuff to the more serious things. Super helpful reminder. Okay, before we wrap up this first part, I got to know more about those bacteria. How do they actually develop resistance to penicillin? It's like they're tiny little geniuses.
It is pretty wild. One major way they do it is by changing their penicillin-binding proteins, those spots that penicillin normally grabs onto.
So they're like changing the locks on their doors so penicillin can't get in.
That's the perfect way to think about it. And if penicillin can't bind, it can't do its job.
It's amazing how these little things can adapt and survive.
They're survivors, that's for sure.
Well, we've covered a lot already this first part of our penicillin adventure.
Yeah, we have.
And we did it all at a beginner-friendly pace, with those handy mnemonics to remember everything. Stick around for part 2, where we'll dive even deeper into the world of penicillin.
Welcome back to Bugs and Beyond. It's really fascinating, to think about penicillin, how complex it is.
It is. I mean, we've already talked about how it was discovered by accident and all that, and how bacteria try to fight back. It's just wild.
Oh, yeah, definitely. We talked about how some bacteria produce that penicillinase, the enzyme that breaks down penicillin and makes it, well, useless.
Right, like they have their own little shield. So are there other ways bacteria resist penicillin? I mean, do they have other tricks up their sleeves?
Oh, absolutely. Some bacteria, like some types of Streptococcus pneumonia, and Neisseria gonorrhea, they've developed this other tactic. They change their penicillin-binding proteins. Those are like the targets that penicillin needs to latch onto to work.
So instead of destroying the penicillin, they just, change the lock so it can't even get in.
Exactly. It's pretty amazing how they adapt like that. They make these little tweaks to their penicillin-binding proteins, and boom, suddenly penicillin can't really affect them as much.
Makes you wonder how they figure that out. That they have their own little science labs going on, trying to outsmart us.
It really is a testament to their survival instincts, I guess.
Yeah.
The good news is we're always learning more about how they do it, which helps us come up with new ways to, fight back.
That's good to hear. So I know there are all these different types of penicillin, right? And each one has its own strengths and, weaknesses. So how do doctors decide which penicillin to use for a specific infection? What are the things they think about?
That's a great question. One big thing is what we call the spectrum of activity. It's basically which bacteria a particular penicillin can actually kill, which ones it's effective against.
Oh, okay. So some penicillins are better at fighting specific types of bacteria. Makes sense.
Exactly. So the natural penicillins, like penicillin G, they work against a bunch of different bacteria, especially gram-positive bacteria, the ones with the thicker peptidog-lichen walls.
Right. I remember. The cities with the strong walls.
Exactly. But they're not perfect, right? We got to remember those resistance mechanisms we talked about.
Oh, right. Those bacteria producing penicillinase and the ones that change their binding proteins. Pesky little things. So what about those penicillinase-resistant penicillins, like oxacillin, nafcillin, and dicloxacillin? Those were the Staph aureus specialists, right?
You got it. And their spectrum of activity is more focused, yeah? They're the ones we use to tackle infections caused by, bacteria that produce penicillinase.
I remember Don. Don't mess with these penicillins.
Exactly. And they're great for staph infections, which can be anything from a simple skin infection to something serious like pneumonia or even endocarditis.
Wow, so they have a really important job. It's like having different teams of penicillin superheroes, each one with their own specialty. But choosing the right one and the right dose, that must be kind of tricky, right? It's not just one size fits all.
Oh, definitely not. It's all about tailoring the treatment to the individual, you know?
Yeah.
So we think about the type of infection, how bad it is, the patient's age, their weight, any other health problems they might have.
Right, right, like kidney problems. It's a lot to consider.
It is, but that's what healthcare professionals are trained to do. They take all that information, plus the patient's medical history and allergies, and then they can decide what the best treatment is. It's really like putting together a puzzle.
That makes sense. Speaking of allergies, penicillin allergy is a big one, right? I
Mhm.
know a lot of people think they're allergic to it.
You're right. It seems like everyone knows someone who's allergic to penicillin. But, the real deal, like a true IgE-mediated allergy that could cause anaphylaxis, that's actually not as common as people think.
Really? So not everyone who says they're allergic actually is.
Nope. A lot of times it's because they had a bad reaction to something else, or they had a mild reaction a long time ago, and it's not really a problem anymore. But it's still super important to know for sure, especially if you've had a reaction before.
So how do they figure out if someone's actually allergic?
Well, if someone says they've had a reaction, we do allergy testing to be sure. Usually skin tests, sometimes blood tests too.
So it's not just like, oh, I think I'm allergic.
Nope, we need proof. And if it turns out they are allergic, it's super important for them to, remember that and tell all their doctors and nurses.
That's good advice. So if someone can't take penicillin, what are their options?
Luckily, we've got other antibiotics that can work really well. The choice depends on a bunch of things. What kind of bacteria is causing the infection, how sick the person is, their medical history, all that jazz.
It's good to know there are other options out there. So thinking about the future, is penicillin still a relevant drug? With all this antibiotic resistance going on, are the bacteria winning?
That's the million-dollar question. It's true that resistance is a big worry, but penicillin is still a super important tool for us. And researchers are always looking for ways to, make it better and develop new versions that can fight those resistant bacteria.
So penicillin's not going anywhere.
No way. It's like constantly evolving, Scientists are looking at everything, tweaking the penicillin molecule itself, combining it with other drugs like β-lactamase inhibitors.
So it's like they're giving it a boost, helping it stay strong.
Exactly. And on top of all that, the hunt for brand new types of antibiotics is still going strong.
That's awesome. It's a constant battle, isn't it?
It really is. And the second part of our deep dive, well, it's given us a good look at how complex it all is, hasn't it?
Totally. We talked about all sorts of things.
Yeah.
Different types of penicillins, the challenges of allergies, and all the amazing research that's still happening. It's been really eye-opening.
It has. And we've learned a lot about how penicillin works, how bacteria try to fight back, and how we can keep using it safely.
But there's still more to uncover. So stay tuned for the final part of our penicillin adventure, where we'll explore even more about this incredible drug. And we're back for the final part of our penicillin journey here on Bugs and Beyond. It's been a wild ride, huh?
It has. From its accidental discovery to, well, all the ways it's still evolving today, it's amazing.
Totally. We've gone from the basics to, all these complex resistance mechanisms, and it's really made me appreciate how much we've learned about this drug.
Oh, for sure. And we've learned about how it actually works, the different types, how bacteria try to resist it. But there's one more thing I think we should touch on before we wrap up. It kind of brings everything together.
Ooh, I love a good wrap-up. Lay it on me.
So remember how we talked about the natural penicillins, like penicillin G, and how they mostly worked against gram-positive bacteria?
Yeah, those were the ones that were good at busting through those thick walls, right?
Right. But what about those gram-negative bacteria, the ones with, well, slightly different walls? Do we have penicillins for those too?
That's a good question. We haven't really talked about those much.
Well, we do, and that's where the immunopenicillins come in. These guys are kind of like modified penicillins, They've been tweaked to work against some gram-negative bacteria too.
So they have a broader reach?
Yep. Think of them as having a special key to get past those gram-negative defenses, like ampicillin and amoxicillin. Those are the big ones.
Ah, okay. So they're kind of like all-rounders.
You got it. And they're used for a ton of different infections, UTIs, ear infections, respiratory infections, even some kinds of meningitis.
Wow, that's impressive. So we really do have a penicillin for almost everything. But I guess even with these newer ones, bacteria can still become resistant, right? It's like a never-ending battle.
Oh, absolutely. Bacteria are clever little things. always trying to outsmart us. But get this, scientists have figured out a way to help the aminopenicillins fight back.
Okay, now I'm really intrigued. Tell me more.
It's all about teamwork. We pair these aminopenicillins with something called a beta-lactamase inhibitor.
Wait, isn't that the enzyme that breaks down penicillin? Like the one those resistant bacteria make?
Ding, ding, ding. You got it. So by combining them, it's like we're giving the aminopenicillin a bodyguard. It protects it from getting destroyed.
Oh, that's smart. So what are some of these, like, penicillin power couples?
Well, there's amoxicillin with clavulin in it. That's a popular one. It's often called augmentin. And then there's ampicillin with sulbactam. That's onicin. They've really helped us stay ahead of those resistant bacteria.
Wow. It's amazing how scientists are always coming up with these new strategies. So it seems like the story of penicillin is far from over, huh? It's still going strong.
Totally. Penicillin is definitely still a super important drug. It's helped save countless lives, and research is still going strong.
It's reassuring to know that we're, well, always learning and adapting,
Yeah.
right? Trying to stay ahead of those pesky bacteria.
For sure. And I think that's the biggest takeaway from all this. The more we learn about bacteria, how they evolve, how we can fight them, the better we can protect ourselves and everyone around us.
Well said. It's been an amazing journey exploring the world of penicillin, from its accidental discovery to all the complex ways it works and how it's still evolving.
Couldn't have said it better myself.
Well, that's about all the time we have for today, folks. Pharmacy to you all, and until next time, keep exploring the awesome world of bugs and beyond.